This is our third lecture in circuit theory, and we have been discussing graph theory, right? We have been working on graph theory, remember, right? We learnt quite a few things in graph theory. We learnt first of all a graph, then we talked about the tree, right? A tree has how many elements? N minus 1, where the graph had n nodes. Then we went further and we talked about links, remember, and how many links? B minus n minus 1 links. Okay. Then we talked about fundamental loops and fundamental cut sets. How many fundamental loops? As many number of links, that is the number of your fundamental loops. So, B minus n minus 1 fundamental loops. Each link corresponds to one fundamental loop. Okay. And then we talked about cut sets, right. This was our cut sets. How many fundamental cut sets? Number of elements in the tree. Each element of the tree contributes to one fundamental cut set. All right. All the other cut sets are combinations of these, union minus intersection. This is what I have written, C2 union C3 minus C2 intersection C3, right. So, you take all these different cut sets, do unions and subtract out the intersection, you get new cut sets, which are not interesting, right. Similarly, you take the fundamental loops, do the unions minus the intersections, you get new loops, which are not interesting. Okay. Only the fundamental loops are interesting, fundamental cut sets are interesting. This is as much as we had done, am I right? Okay. Now, what we are going to do is, we had even written one of these as a set of KCLs, right. We had taken this graph and we had taken these fundamental cut sets and we had written it up as a set of KCLs. All right, any questions about this matrix equation? No, these are all KCLs. I A plus I H is equal to 0. That is what the first line is. First row corresponds to I A plus I H is equal to 0. The second row is I B minus I C plus I H is equal to 0. The third row is minus I C plus I D plus I H is equal to 0. The fourth row is I E plus I F minus I H is equal to 0, and the fifth row is minus I F plus I G is equal to 0. Okay, these were all the KCLs. Fine. So, like this you can organize your KCLs as a matrix. Note that this matrix, in this matrix equation there is one big matrix, that big matrix only has ones, minus ones and zeros, nothing else, right. There is no 2, there is no half, there is nothing. It is either a plus 1 or a minus 1 or a 0, fine. That is the structure of the matrix. All right. Now, what we are going to do is, let us have a simple graph, and I am just taking a new graph, because I do not want to do too much work. How many nodes, how many branches? N is equal to 5 and B is equal to 7. So, just keep that in the background, N is 5, B is 7. So, how many fundamental loops? B minus N minus 1. So, 3 fundamental loops and how many fundamental cut sets? 4. Just keep this in mind, okay, before we start. All right. Now, I am taking a step backwards, all right, and what I am going to do, oh by the way, I can't and do any KVL KCL unless I put arrows. I have to make it a directional graph, right. I have to put some arrows over here. So, let me just indicate some, just give some direction to all the branches. Okay. So, now I am going to take a step back and I am going to say that all of this tree, branch, cut set, link, all of that is too complicated. I am getting a headache with all of that tree, and it itself was a lot of work, right. It was a lot of work. So, I do not want to do all of that. I just want to go to each node and write out a KCL at each and every node. So, for example, I will go to node 1 and write out a KCL with that cut set, and go to node 2, I will write out a KCL, go to node 3 and write out a KCL, go to node 4 and node 5 and write out KCLs at each of these individual nodes. Okay. So, let us do it, and the way I am going to do it. So, how many KCLs am I planning? 5. Okay. So, let us just go to node number 1. At node number 1, you see that the total current going out of the node is minus I A plus I F plus I E. Okay. So, minus I A plus I E plus I F is equal to 0. Is this okay? Any questions? Writing it in this form, right? Matrix multiplication is implicit, right. I am assuming that you know how to multiply matrices, right. Row wise minus 1 times I A plus 0 times, it is not required, right. And then the next time it comes, it is 1 times I E, next time it comes, it is 1 times I F is equal to what is on the right hand side? 0. Fine. So, this is how I am going to write it. Then let us go to node number 2. At node number 2, I have I A minus I B plus I G, no, I A minus I B minus I G is equal to 0. So, I A minus IB minus IG. Fine. Then I go to node number 3. At node number 3 I have, somebody tell me, IB plus IC is equal to 0. So, IB plus IC is equal to 0. Then node number 4, minus IC plus ID minus IF plus IG is equal to 0. Okay. And lastly at node 5, minus ID minus IE is equal to 0. Is this okay? Any questions? No. What do you see? Is this now? So, this particular matrix, this is going to be called the incidence matrix. Okay. The incidence matrix is full of values. How many rows does it have? How many columns does it have? N rows, B columns. Okay, it has B columns, N rows, fine. And the elements in the incidence matrix can be either 0 or plus 1 or minus 1. These are the only possible values, fine. Nothing else is possible. You can't have minus 2. Okay, good. Now, tell me, are these linearly dependent or linearly independent? Dependent. Why? No, no, forget KVL. There is no KVL. We haven't done. These are 5 equations. Are these 5 equations linearly dependent or linearly independent? Dependent. You are all saying dependent. And Arman, Adib says that it is more than the number of fundamental cut sets. So, the number of fundamental cut sets was n minus 1. So, 1 less than this, okay. And therefore, this cannot possibly be linearly independent, because I am sure I have at least one extra equation, if not more. Can you tell me? For example, if I add up all the rows, what do you get? If I simply add up all the rows, no, just add all the rows, 0. What do you observe in each of these columns? Each column, look at each and every column, there is a structure. What do you see? Each column has only one entry which is 1 and only one entry which is minus 1, and all the others are 0. So, if I look at any of these columns, right, there is just 1 1 and 1 minus 1. Every column has a single plus 1 and a single minus 1, and naturally the column adds up to 0. Every column adds up to 0. So, obviously Adib is right, it is linearly dependent, right. They are all adding up to 0. So, you can't really do anything, this is not solvable. This is a bad set of equations. Okay. But look at the structure, every column has a single plus 1 and a single minus 1. Can you tell me when is it plus 1 and when is it minus 1 and when is it 0? Let us examine a single column, right. Let us say I want to examine this column C. This is the column for C, right. Okay. Let us examine the column for C. When is it plus 1, when is it minus 1, when is it 0? Your name is Sagar, Kushagra. So, Kushagra says that if I look at branch C, branch C started from node 3 and therefore, its node 3 branch C started from node 3 and therefore, node 3 is a plus 1 and branch C went to node 4 and therefore, node 4 is a minus 1. Okay. And branch C can't start at more than one node. So, therefore, there is only 1 plus 1 and branch C can't end at more than one node. So, therefore, there is only 1 minus 1 and therefore, every column adds up to 0 guaranteed. Fine. Wherever it starts from, it is a plus 1, wherever it ends, it is a minus 1. Fine. Look at the structure, it is quite nice. The structure of this matrix is quite nice, right. So, this is called the incidence matrix and unfortunately, so in short we write it as AI. AI is known as the incidence matrix and this is what it is. You just go to every node and do a KCL at that node. All right. What it gives you is the incidence matrix. All right. Now, the incidence matrix, as it has been pointed out, is not very useful, right. It is rather useless in fact, because it is all linearly dependent. So, we can't deal with it. So, what I would like to do or what people then did is they just removed this last one. They just said that this last one is probably extra. Okay. Remember the number of cut sets, fundamental cut sets was n minus 1. So, there was 1 extra, here there are n. So, let us remove this last one, let us just throw it out, right. Arbitrarily we choose the last one, actually it is not so arbitrary, right. We are going to, instead of calling it 5, I am going to call it 0. We are going to call it the 0th node, all right. Some people call it the reference node, some people call it datum, some people call it ground, and some people call it earth. All synonyms. Okay. For us, these all mean the same thing, all 4 words mean the same thing for us. What are we doing? We have simply taken the last row and said, I do not care what happens over there, I do not need it. We are going to call this extra, all right. And this last node, instead of calling it node number 5, I decide to call it node number 0. Okay. Not just that, I am going to assign it a potential also later on of how much? 0 volts. I will assign it a potential of 0 volts later on, not yet. This is the plan. Fine. Now, if I throw out this last row, what happens to the rest of the matrix? Is it going to be dependent or independent? How do you know that it is independent? Can you prove? That is fine. Can you prove? How do you prove linear dependence? So, you just take the rows, right. These are my rows, row 1, row 2, row 3, row 4, row 5 is now ignored, right. And let us say I have these non-zero constants k 1 times row 1, k 2 times row 2 plus k 3 times row 3 plus k 4 times row 4. I have to find k 1, k 2, k 3, k 4 such that this sum is equal to 0. Okay, if I can do this, then it is linearly dependent. If I can't possibly do this, then it is linearly independent, or to do this, if k 1, k 2, k 3, k 4 all have to be equal to 0, right, then it is linearly independent. Fine. So, this is the test for linear independence. So, let us try to find out k 1, k 2, k 3, k 4. Can you prove that you can't possibly do this? So, remember, go back to the structure, right. So, if I look at this one, then this one is balanced by a single minus 1. All right. So, if I need this answer to be equal to 0 and k 4 is not equal to 0, can I have this answer to be equal to 0 with k 4 not equal to 0? K 4 has to be equal to 0, otherwise this answer is never going to be 0. You see this? Look at this one, all right. This one is balanced by a single minus 1 on the bottom row, correct. And therefore, if I need this sum to be equal to 0, then k 1 has to be equal to 0, there is no other way, and there you go, right. There is no way to choose k 1, k 2, k 3, k 4 such that they are not all equal to 0 and make this true. Fine. So, therefore, and this is going to happen, right, whenever I mean whatever graph I draw, the last one will have some connections to it, and therefore, you will be making it linearly independent now. Fine. All right. So, this new matrix is called the reduced incidence matrix. So, let us copy this over to the next page. Alright. So, this new matrix with the last line scratched out, this is going to be called the reduced incidence matrix okay. And since this is a very useful one, this is a useful one okay. The previous one was useless. So, we call it A, capital A okay, capital bold yeah. You can do that also. You can choose any one node as ground or the reference, any one node you can remove that. I have simply removed the fifth one because that was at the bottom, right. And you see deliberately when I drew the circuit, I made 5 at the bottom. Okay. So, it is okay. You can choose whichever, you can choose any one of them to be ground, it does not matter. So far so good, any questions? So, A, the reduced incidence matrix, this is linearly independent. This is a set of equations which are linearly independent and we like this. Alright. I am going to write this matrix equation as follows: A times I is equal to 0 and here capital A is the reduced incidence matrix, capital I is what? This is I, right. It is a vector, it is a column vector with all the currents and the 0 is a vector full of zeros. It is not a single 0, it is a vector full of zeros. Okay. You are all comfortable with matrices somewhat, multiply you can do. Okay, good. All right. So, now this is my setup. Okay. Now, what we are going to do is we are going to define the following. We are going to define the voltage at each of these nodes, all right. And at node 0, I am going to call it 0 volts, just because I have called it 0, it is ground. Okay. So, we are going to call it 0 volts, node 0 voltage is 0 volts. Node 1, the voltage I am going to call it as V 1, then V 2 at node 2, V 3, V 4, fine. And then what is V A? What is the what is the voltage of branch A, V A? Yeah, in this graph, louder, V 2 minus V 1. So, whichever is higher that is the start of the arrow, whichever is lower that is the end of the arrow. So, it is V 2 minus V 1. Okay, the voltage drop is going to be in the same direction as the current. Okay, so, we are going to call it V 2 minus V 1. So, let us write this out. I want to write this out. So, V A is equal to V 2 minus V 1 and similarly V B, V C, V D, all right, all those, but I do not want to write it out like this, right. By now, you know that I do not write out 7 equations. Okay, what will I, how will I write it out? As a single matrix equation, thank you. Okay, so, that is my plan, I do not want to do this mess, all right. So, we are going to write it out in this fashion. Fine. Let us make these bigger. Okay. So, V A is V 1 minus V 2, no V 2 minus V 1 is V A. So, V 2 minus V 1 is V A. Okay. Any problem? No. And then V B, V 3 minus V 2 is V B, V 3 minus V 2, and then V C is V 3 minus V 4. Okay. Hang on, go with me, this is not boring. Okay. We are there, some magic is going to happen now. Okay, wait for it. So, this is V C, V D, what is V D? How much is V D? V 4, V 0 is 0. And then V E, V 1. And then V F 1 minus 4. And lastly, V G, G is okay. So, I have constructed all of it. Now, yes, I heard that. Yeah. All right. Tell me, are these two gigantic matrices related to each other? And Adib has already told me they are transposes of each other. Is this always true or just a stroke of luck? Okay, your name is Nishant. Nishant has some logic, although I do not fully follow. Anyone else? But it sounds like you know what is going on, but not articulate enough. Okay, thank you, good. So, in the first matrix, if you saw, if you inspected every column, right, there was an origin, there was an end. The origin was a plus 1, the end was a minus 1. Okay. Here the column has become a row, right, the same row, starting point, ending point, plus 1, minus 1. Is it okay? So, therefore, this matrix is nothing but A transpose. Fine. So, every time you started from a particular node in the original one, right, the current started moving out. here the voltage starts voltage starts with a plus sign, right. Current starts moving in, here the voltage comes with a minus sign, that is all. Alright. So, whatever was a column in the previous matrix has now become a row in this particular matrix, and therefore, A and A transpose are transposes of each other. Fine. So, we are going to call this A transpose, and instead of writing all of this, we are going to write it out as A transpose times E is equal to the vector with all the voltages V. Fine. All the branch voltages, we call it the vector V. Any questions so far? Great, because now comes a very important theorem called Telegon's theorem. So far everybody has understood? So, Telegon's theorem states that V transpose times I is always equal to 0, and this indicates V transpose means V is a column vector with all the voltages. So, V transpose is a row vector. So, row vector is V transpose times a column vector I. So, V transpose times I means the dot product of the voltage vector with the current vector. It is a dot product. Okay. Dot product of all the voltages with all the currents. Nothing new. It is nothing new, is it? Okay. So, a lot of people seem bored, right. This is not new, this is nothing, this is sum of all the voltage times currents is equal to 0. Yes, this we knew in class 12. This is also called law of conservation of energy, very good. Law of conservation of power in this case, right. Power is neither produced nor destroyed, right. Wherever somebody has to generate, somebody is going to consume. What you have to appreciate in this case, that this particular theorem is much bigger, much wider in scope than the law of conservation of power or energy. First let us prove this. Okay. First let us prove this. The proof is very straightforward, right. If you have understood everything so far, then you know that V is equal to A transpose times E, this one, all right. So, therefore, V transpose is nothing but E transpose into A, and then times I, right, and in the previous page you have got what? You have got A I is equal to 0 because of KCL. So, therefore, it is equal to 0. So, the proof is ridiculously straightforward, okay. It is too easy in fact. Fine, okay, good, because Telegon's theorem is valid even if the two circuits are different. So, I could measure the voltages on one circuit, and I could measure the currents on some other circuit and take the dot product of them. They have to have the same graph, okay. Same graph has to be there. Two circuits having the same graph, same topology. Same graph means this is the same, this structure is the same 1, 2, 3, 4, 5 arrows, directions of all the arrows, nodes, this is the same. In circuit number 1, I can have resistors, diodes, voltage sources, capacitors. In circuit number 2, I could have inductors, transistors, MOSFETs, something else, okay, nothing stopping me. But what do I see? I measure the voltages on circuit number 1, right. I measure the currents on circuit number 2 and do the dot product. That dot product is going to be equal to 0. Why? Because the matrices are the same, the matrices have no knowledge about what is inside the circuit, it is either plus 1 or minus 1 or 0, right, that is it. It does not care ohm, right, forget ohm, forget Tesla, all those guys, you do not need anybody, right. You only have KCLs and KVLs, right. As long as the circuits obey KCL, which is all the time, right, all circuits obey KCL. So, therefore, this incidence matrix is going to be the same for both. Two circuits will have the same incidence matrix, right, and therefore, this also is going to be the same, A transpose is also going to be the same, because they also obey KVL, which means that V A will always be equal to minus V 1 plus V 2 and so on, right. So, as long as they obey KCL and KVL, right, I can measure the currents in one circuit, I can measure the voltages in the second circuit, do the dot product and they should be equal to 0. Agreed? I can take the same circuit at different times. I can do a measurement at t equal to 0 for the voltages and I can do another measurement tomorrow for the currents, and then the dot product is going to be equal to 0. All right. So, this is much more what Telegan's theorem is, it is way more than what you have done in class 12, which is law of conservation of power in this case, right. The power does not matter, right, power is just one special case of this, right, where you are doing the two measurements on the same circuit at the same time, correct. But you could have the same circuit, change some component values, right, operate the circuit under different conditions, change the temperature, change the value of the voltage source. Telegan's theorem is going to be valid. You measure the voltages at one time, measure the voltages for the second time, do the dot product, it is always going to be equal to 0. Okay. For those who think of vector spaces, yes, no, okay, fine, we will leave that. These are basically orthogonal vectors. When you do a dot product of two vectors and you get 0, what does it mean? The angle between the two vectors has to be 90 degrees. So, the voltage vectors and the current vectors are always at 90 degrees from each other, perpendicular to each other. Okay. So, I am expanding the scope of, anyway, it does not matter. Understood? Any questions? This is a very important theorem, Telegan's theorem. Sometimes when all is lost, you just do not know how to solve the circuit. Application of Telegan's theorem might save you, right. All kinds of situations, suddenly Telegan's theorem will pop up and save the day, and you will suddenly realize that, oh, this is true because Telegan says so. All right. So, Telegan's theorem makes no assumption of what components are there in the circuit, right. It makes no assumption of anything linear, nonlinear, time invariant, nothing, no assumptions made. Only assumption is that the graph is fixed, okay, and KVL, KCL is not an assumption, it is a law. So, as long as the graph is fixed, right, Telegon's theorem is going to be valid. Fine. Okay. So, with this we are going to move to our first circuit solving method. This is called the node voltage method. And what we are going to do is, we are going to do which strategy? We will not do all that tree and so on, we will do this strategy, this, right, or rather this one, right, where we choose one node as ground or reference, one node we choose as the datum, and at each of the other nodes we go to each of the other nodes and we do a KCL. Okay, we are going to perform a KCL operation at each of the other nodes and then try to see if we can solve it, solve the circuit. So, this is the plan. So, the node voltage method is going to use only KCL. So, even though this is node voltage, we are only going to use KCL. Okay. Let us do an example. Too many. You wanted the same graph as there before? Yeah, it is too much. We are making a fresh one, right. Otherwise, I will have to keep copying the graph again and again. Let us just do one new. Okay. So, this is my new circuit. It has nothing to do with the previous graph, but there seem to be how many components? 8 components. All right, and how many nodes are there? So, let us label this as this is the symbol for ground. Okay. So, we are labeling this as having how many volts potential? 0 volts. We are not going to solve at this node. Fine. And then let us label this as V 1, V 3, V 4. Fine. Have I missed anything? So, there are 4 nodes and 8 branches. Okay. It is not 4 nodes, 5 nodes, because ground is also counted as a node. So, 5 nodes, 8 branches, and therefore, how many fundamental cut sets? 4. All right. So, what we plan to do is, we plan, instead of thinking of fundamental cut sets, we ground one node and we are going to do a KCL at node 1, a KCL at node 2, a KCL at node 3 and a KCL at node 4, and my n minus 1 condition is automatically satisfied. I do not want to do a KCL at ground, that is ignored. This is the plan. Okay. All right. So, when I say we are going to write the KCLs, we are not going to talk about the currents at all. Okay. In fact, I am not going to talk about IA, IB, IC, ID, not there. All right. Let us see how we do it. So, we go to node number 1, and node number 1 has total current flowing out of node number 1, okay, has 3 branches. One current goes out through R 4, one current goes out through R 6, and another current goes out through I naught, correct. What is the current that goes out through R 4? V 1 by R 4, thank you. What is the current that goes out through R 6? V 1 minus V 2 by R 6. All right. This is how we are going to think of the currents. Okay. No symbol called I A, gone, that time is over. Understood? All right. So, this is the first order of jumping. Next order of jumping steps is the way we are going to write it. And as you have realized by now, what have you realized by now? When I have to write lots of equations, I am only going to write them as a matrix equation. Okay, I am not going to write V 1, V 2, V all the different things. No, it is always going to be in the form of a matrix. And here my unknowns are V 1, V 2, V 3 and V 4, and that is it. Okay. Eventually, when somebody asks you to solve a circuit, what are they asking for? They are asking for all the voltages, all the branch voltages and all the branch currents, but we do not want to do all of that. Okay. We are going to take a shortcut. We are only going to compute V 1, V 2, V 3, V 4, because the branch currents can be worked out. If I know the 4 voltages V 1, V 2, V 3, V 4, I can work out all the branch currents. Yes. So, I do not want to think of the branch currents at all. In fact, I am going to leave it and say that a good calculator is all I need to compute the branch currents. Okay. So, forget it. Okay. What about the branch voltages? Same, they are just differences. Okay. So, those also we are not going to work on. We only are going to work on V 1, V 2, V 3, V 4. Okay. So, this is the setup. Now, we go to node 1. So, V 1 by R 4, please jump with me, V 1 by R 4 plus V 1 minus V 2 by R 6 plus I naught is equal to 0. Okay, I am saying something, I am writing something else. So, please pay attention how I have jumped. I have jumped multiple steps and done a rearrangement. Okay. I have moved I naught from left hand side to right hand side, right, and I have grouped the terms in a way that the matrix multiplication happens. I have grouped the V 1 terms together, right, the V 2s together, right, all the groupings have been done. Is this okay? Is this first sentence clear? Clear? Okay. Next we move to V 2. When I go to V 2, I see that V 2 minus V 1 by R 6 plus V 2 minus V 3 by R 1 plus V 2 minus V 4 by R 5 plus V 2 by R 7 is equal to 0. Is this okay? You guys have to practice, all right, practice these leaps. This is not a jump, this is a leap. Okay. So, learn how to take these leaps. Next, I go to node 3, and at node 3 what do you see? I see V 3 minus V 2 by R 1 plus V 3 minus V 4 by R 2 minus I naught is equal to 0. Okay. And lastly, I go to row 4, node 4. And at node 4 what do you see? At node 4 you see V 4 minus V 3 by R 2 plus V 4 minus V 2 by R 5 plus V 4 by R 3 is equal to 0. Fine. Any questions? All of you are comfortable with this fast moving circuit analysis? All of you are comfortable? And then how do you solve the circuit? Take the inverse of this matrix, multiply it on both sides of the equality, right. I get V 1, V 2, V 3, V 4 is equal to inverse of this matrix times minus I naught 0, I naught 0. Okay. This circuit analysis technique is called the node voltage method, right. We exclusively use the KCL and device properties. KVL, what about KVL? Did we use KVL? KVL is built in, it is inbuilt. How? Where did KVL go? KVL went into the fact that the drop across R 1 is V 3 minus V 2, that is your KVL. Okay, it is inbuilt. The way we have done it, you do not have to write any KVL at all. KVL is already inside the system of equations. Okay. So, you do not need to worry about KVL at all. Fine. So, this is called the node voltage method. Let us complicate matters a little bit, right. This was so easy, right. This was easy or no? This was easy. Okay. All you need is a little bit of practice and you will be able to write out the matrix setup by inspection. I need you to be able to write the matrix by inspection, like we did. Okay. You have, I mean, you have to practice a little bit, just little bit practice, you will figure out. Any sanity checks? Sanity checks? What is a sanity check? Verify that things are sane. That is called sanity check. Yeah. Any sanity checks that you can do? One sanity check is that the matrix is symmetric. Is it? It is symmetric, is it? Why? Why is the matrix symmetric? It is not symmetric or it is? It has got to be symmetric, that is my sanity check. Okay. Why is it symmetric? I will not answer the question why right now. Okay, we will see it much later. Next sanity check is that all the diagonal elements are positive. All the others are negative, or 0. So, the diagonal elements are positive, the others are negative or 0. Is that okay? You have a reason why that happened? Why did that happen? Okay, very good. Your name is? Nishant is absolutely right. So, the diagonal elements, we always started from the diagonal element, right, and then wrote the other element as negative. Okay. So, the diagonal will come to be positive, all the others will come to be negative, and the big sanity check over here is that the matrix is somehow magically appearing to be symmetric. Okay. Why, you can think about it. I will answer the why later after many more lectures. I will answer it after a while. For now, this is a sanity check for you. Okay. Now, we are going to complicate matters. By the way, did I need this current source? Could I have had a resistor over there? Yes. If I had a resistor, then my answer would have been equal to 0. I would not need to invert any matrix. No, solution would be exactly equal to 0 for everything. Okay. I needed that current source. Okay. I needed a source. Without a source of power, your answer is going to be 0. Okay. You do not need to do any computation. All right. What I am now going to do is, I am going to replace this current source with a voltage source, and that seems very reasonable thing to do. Just that my node voltage equations are going to become very difficult now. Why? So, if I go to V 1 and try to do a KCL, I just will not be able to do that KCL, Do you see that I can't do a KCL? Why can't I do a KCL? Because the branch with the voltage source, the current is not known. Okay. So, I can't do a KCL at V 1. So, I am stuck. What about V 3? V 3 also gone, I can't do it. V 2, V 2 remains the same, and V 4 is also the same, only V 1 and V 3 are affected. So, this row is wrong and this row is wrong, fine, the other two rows are the same. Okay. What do we do? Now, I have 2 equations and 4 unknowns, 4 unknowns, right, V 1, V 2, V 3, V 4. V 1 and V 3 are related to each other. How are they related? V 1 is nothing, sorry, V 3 is nothing but V 1 plus V naught. So, in fact, you can now delete V 3 and write it as, sorry, simply rewrite V 3 as V 1 small v 1 plus capital V naught. Okay. We now have a system with 3 unknowns, not 4. So, V 3 is gone, V 3 is not even an unknown. Okay. So, V 3 is not an unknown, I do not need this equation. I can't anyway, I can't write an equation at V 3. V 4 the equation is correct, but V 3 has disappeared, right. So, it will be minus 1 by R 2 times V 1 plus V naught, fine. So, how do I write it? Minus 1 by R 2 times V 1 minus 1 by R 2 times V naught, which goes to the other side. This is okay? This last row is okay? Is the last row okay? Okay. And the second row, let us fix the second row. The second row says minus 1 by R 1 times V 3, but V 3 is nothing but V 1 plus V naught. So, it is minus 1 by R 1 times V 1 minus 1 by R 1 times V naught. Is this okay? Okay. This is also good. So, I have 2 solid equations, right. The third row has disappeared and the first row is also a question mark. The first row is also wrong, this is wrong. Let us rub it off, because anyway I can't do a KCL at V 1. So, what do we do? Anyone? Anyone? Thank you. Your name is? Arzan. Arzan has given me the final answer. What we are going to do is, we are going to have a cut set, not my individual node anymore. Okay. What we are going to do is, we are going to join these 2 nodes into one great node, right. This is my cut set, and now the KCL for this cut set is equal to 0. The current coming out of this enclosed area is equal to 0. So, let us write out V 1 by R 4 right. This is V 1 by R 4 plus V 1 minus V 2 by R 6, correct, plus V 1 plus V naught minus V 2 by R 1 plus V 1 plus V naught minus V 4 by R 2 is equal to 0. Fine. So, this is going to be my third equation, in fact my row number 1. Is this okay? Yeah, it looks horrible. Can you read what I have written? So, I have grouped them and rearranged them, all jumping steps. Okay, you have to group, regroup, rearrange, substitute, all of those have to happen. All right, but the good news is it is one less equation. So, earlier it was 4 equations, 4 unknowns, now it is 3 equations, 3 unknowns. Okay. So, every time I am adding a voltage source, if I add one more voltage source, what is going to happen? One equation will go, okay, because now wherever the voltage source starts I can't do a KCL over there, wherever it ends I can't do a KCL over there. So, those two equations will be out, but I can combine the two and write a single KCL, fine, and then the two nodes are going to be related to each other. So, I will have one variable less, fine. This is the plan, this is how we are going to do it. All right, quick question for you. I have a graph and in the graph I have n nodes, b branches. How many elements are there in the tree? N minus 1. Okay. Now, can I have more than n minus 1 voltage sources in my circuit? This is the question for you. You are shaking your head, why? No, 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 we are not creating the graph. The graph exists, I am just placing voltage sources for each branch one by one. I am replacing each branch with different components. My question to you is, can I have more than n minus 1 voltage sources in my circuit? Thank you. I can't, because the tree has only n minus 1 branches. So, the nth branch will always be a link. So, and therefore, I will end up having voltage sources in a loop. I will create a loop of voltage sources. So, the maximum number of voltage sources in the circuit is n minus 1. Suppose I have exactly n minus 1. What was n in this case? In this case? No, no, in this example 4. So, n was 4. So, can I have 4 voltage sources? No. 3 voltage sources you can have, not 4. No, you can have 4 voltage sources, just that you will have nothing to solve. Okay. So, every time I am throwing in one more voltage source, I am getting one equation less, one variable less. So, 1 voltage source, only 3 variables left, 2 voltage sources, 2 variables left, 3 voltage sources, 1 variable left, 4 voltage sources, nothing to solve. Okay. For example, I could have this as a voltage source, this as a voltage source, and this as a voltage source, right. Immediately V4 is self evident, because it is ground plus the voltage source corresponding to R3, right. V2 is also self evident, because it is V4 plus the voltage source in place of R5, and V1 is also self evident, because it is V2 plus the voltage source corresponding to R6, and then V3 is already V1 plus V0. Okay. So, there is nothing to solve, you do not have to write any matrix, right, because it is already solved for you. Fine. The voltage sources have to be on the tree. Are we clear? The voltage sources have to be on the tree of the graph, they can't be here and there, they can't be on links, they have to be on the tree of the graph. So, when you choose, if at all you choose a tree, right now we are not choosing trees, we have just gone with the flow and done the node voltage method. But if at all in future you want to choose the tree of a graph, then where are the voltage sources? They have to be on the tree. Okay. If I have talked so much, then what about the current sources? Right. So, if the voltage sources have to be on the tree, then the current sources, they have to be on the links, okay, because you have to make sure that you do not do a KCL with only current sources, all right. And if you have more current sources than the number of links, how many current sources? So, what is the maximum number of current sources? The number of links is the number of maximum number of current sources allowed in a circuit. So, in this case it would be B minus n minus 1. How many? N was 4, B was 8, is it? Okay, I have forgotten what is B. B must have been 8, R 7 and V naught, yeah. So, 8 minus n minus 1 was 4. So, 4, n was 5. No, n was 5, n minus 1 was 4, n was 5. Okay. So, the maximum number of current sources is 4 in this case. Fine. Any questions? You will end up with a KCL with only current sources, and that is illegal. You can't have a KCL with only current sources. Okay. You can't have a KVL with only voltage sources, you can't have a KCL with only current sources. Okay, any questions so far? This is okay, node voltage method is okay, the way I have combined nodes is okay. So, this is called a super node, just by the way. So, if someone says what did you do, describe the method. So, you are going to say I am going to make a super node, it is not really a node, it is more like a cut set, it is more like a Gaussian surface or a cut set, right, super node. So, you are basically making a super node, which is you are basically combining, you are encompassing the entire voltage source, you are eating up the voltage source inside the cut set. Fine. So, when we have the current sources, the good news is that writing the equations is easier. When we have voltage sources in the node voltage method, writing the equations becomes a little harder, but number of equations goes down, okay, number of variables goes down. All right. So, with this we are going to close, and in the next class we are going to study the other method with the loops. This was with KCL. Now, we are going to do KVL, right, that is called the mesh method. So, that is what we are going to do in the next class. Thank you.